Sí, este tiene más. ¿Cómo se carga, Jorge?
How does it work? This way is off for the... Okay. Okay. Do I have a device for paging down the slide? Yeah. As is mouse, okay. Oh. Is it mine? Yeah. It is not yours. Yeah, okay, okay, okay. Wer? Technische, ja. Morning. Your FPGA solution. Can you explain how it works? Because I would also like to briefly present what we are doing.
Let me try to explain here what I have. Julia.
Papa, ich habe jetzt Konferenz hier.
Eckhard, hörst du mich? No? Cannot hear me?
Ja, ja.
Du hörst mich gut.
Ja, ja. Hörst du mich auch?
Ich höre dich auch sehr gut, ja.
Ja, gut, gut. Und ihr habt noch ein bisschen Pause oder was fangt ihr an?
Wir fangen dann um 12 Uhr, wollen wir anfangen. Wie spät ist denn jetzt? Oh, ist ja schon vorbei.
Danke, dass
What about the other virtual participants? Do you know? How?
Sind schon der Oliver Rettig und der Zhaoyuan, die sind da.
Okay.
I am trying to now make the VHDL and the IP code.
What do you want to make one?
The VHDL. I have some VHDL code already with the. We have some using the Simulink. Let me just open it here maybe. Yeah. Yeah, cool.
Oh wow.
Yeah. Then, for example, we have this function. It evaluates the curvature, the Darboux projections into multiple axes in the three-dimensional system. Then there are three parts. Yeah, let me just make it the most graphical style that is basically this look is right now we are in this first phase. No? These are very just this year. Then this is the FPGA we are using right now at the moment because I easy can carry this.
You have it with you.
Yeah, and then no, I didn't bring the other because I leave it at home. I can install also Linux here. I have this. I don't know if you have heard about this pin. This is to handle layers. This solution. Yeah, Python. You can use Jupyter and then deploy also FPGA acceleration systems and then engage them with the software based on Python that it will allow you to work fast. Yeah. Instead to use operating system of C. But for example, in bit.
So you do not have to program hardware description language.
Yeah, you program the hardware description language. You create, you know what is the IP core or what kind of FPGA do you?
Xilinx.
Yeah, this is Xilinx, and then for example with the IP core, you can deploy the IP core, but then link it with the processor.
Yeah.
I don't know where Jaroslav and Alex. I'd say let's wait for a minute.
Then here it opens the module. This is an example. This, for example, I have this module. I have the data for the test. I just scale it down to have a lower computation because I can use say floating point libraries. Right now here we have the derivative part.
Okay, let's discuss later. And I think we have to start, isn't it? I need my mouse. Okay. Oops. Okay. One. Why? Why? Okay. Okay, welcome everybody to our session about geometric algebra computing centers. I hope the virtual participants can also understand me. Can you?
Yes, that's fine.
Okay, fine. So, first of all, what are the goals of geometric algebra computing in principle? The focus is not so much on the geometric algebra itself, but on computing with geometric algebra. Means the focus is on high runtime performance, robustness of the implementation, support of many programming languages is very important, as well as the support of different computing architectures. And the question is in this area, what is the best to use? In which case, if you have a specific application, what is the best tool to use? And why do I think that we need this geometric algebra computing center? So the current situation is still that the community dealing with geometric algebra and geometric algebra computing is very small. We have many different computing solutions, specific solutions with very specific applications. Our focus is very much on papers, means our focus, sure, at academia, that's a very important request to have as many papers as possible. But for engineers or for programmers, it is not so easy to extract the information that they need out of papers. And we already discussed yesterday, we have so many notations. And we have to simplify that in a way that also engineers can easily understand. And talking about computing, a very important thing is, I would say, the different point of view of mathematicians and engineers. So in my geometric algebra computing lecture, I always had participants from mathematics as well as from computer science. And in this lecture, I realized that the point of view is completely different. The mathematicians were in a first step interested in the mathematics itself, learn to understand what's behind this algebraic system and so on. And only in the second step, they are interested in application. What can I do with it? And the computer science point of view is completely different. They first want to see what can I do with this system, and then in a second step, they are motivated to go also into the theory. So it's completely different. And my feeling is that we do not very much provide information that engineers or computer scientists need. And this is why I think we need this center. So what's to do? For instance, it is very important to spread our knowledge. I made an interesting experience 2 weeks ago in the discussion with Harris, who just made his PhD in Cambridge. He made his application was a point cloud registration. And this application is very compute intensive. And he knew MATLAB and wanted to use MATLAB. And in order to deal with geometric algebra, he knew that there is the Clifford multivector toolbox for MATLAB. It is well known from many papers, and this is why he used it and was not aware that there are also other possibilities. Means we do not have some kind of common knowledge. What can I use if I want to use this programming language also? So we talked about this paper. It is a paper of us together with the people from Brno. It was with Rettig, and we used our tool GAALOP or GAALOP Web, the online version, for MATLAB, because we also have a MATLAB solution, but I have the feeling that nobody knows it. And they also used the MATLAB toolbox first, and then they realized they have problems with performance. And then we developed this GAALOP Web also for MATLAB. Oops. Okay, this is the application, industrial robot, and there was a geometric algebra algorithm describing the forward kinematics in this example of the robot. And here you can see the code of the toolbox, and on the other side the code of GAALOP, and you can see it is very, very similar. The main difference is that the toolbox is a library, and library means you have to compute everything, every operation, for instance, the tool or the wedge or whatever you need. You have to compute it on the machine. And what we do is first to optimize this code. And no, it was too fast. Okay. We first optimize the code, generate optimized MATLAB code. And for instance, there was a variable R1. This does not have to be computed. I do not know what the operation behind was, but only the final result is pre-computed. And the same for this variable P2 help, and so on. And you see the remaining operations are very simple. We only compute the coefficients of the multivectors which are needed, and in a very optimized way. Means everything is, as far as possible, pre-computed. And then the surprising result was this. In principle, we were 1,000 times faster. Means this is a really a big difference. In principle, we have the same code, but 1,000 times better run times means if we have an implementation needing seconds in using our tool, you need only milliseconds, and this is a big difference. And what I wanted to say is that Harris didn't know that, and we do not know what the result will be then with MATLAB. It will not be as good as in this implementation, but I'm very sure it will be better. But he didn't know, and this means he made some runtime comparisons, and his solution was similar to the standard solution currently, but with some speed up, he can show my solution is much better than the other one. But currently, he can only say it is similar performance, and this is a big difference, I would say. Okay, then another discussion of this week with Santiago. Also, we have an FPGA solution, and Santiago is also working on FPGA solution, but we didn't know this from each other. Means also in our community there is a lack of information. What tools do we have, and so on. So what we realized is a standard FPGA design called GAALOP, and with this design we can also use our GAALOP tool. Means we can describe an algorithm in GA, and then we generate configuration data for this FPGA, and the FPGA can then immediately realize the new functionality. So this is the principal design of GAALOP. We realized that in principle, if the code of a geometric algebra algorithm is optimized, we only have sums of products. Very, very simple expressions. And this is why we mainly need these dot vector units. And we have to simply configure this FPGA then with a new algorithm, and that's it. And then the FPGA is working with a new algorithm. Okay. So I think one very important goal of this computing centers should be to spread the knowledge of geometric algebra computing, and we somehow should have a common knowledge base. What's available, who is the contact person, and whatever. And we also should, you yesterday talked about that, we should have some kind of educational tools. Maybe videos, whatever, I do not know, but some information who make it easier to know what's available. And in order to broaden our knowledge and our experience, I think we should attract industry. That's very, very important. In order, we are very convinced of what we are doing, but it is not really used in industry until now. And this is why I think we should somehow provide easy solutions for industry, that they do not have a big learning curve and need much time, but easily can use what we are providing. Yes, we should have intelligent tools, frameworks for programmers and for industry and for education. Between the centers, I think it's important to have common topics, to write common papers, to use synergy effects, and you yesterday mentioned success stories are somehow very important in order to attract people and to give them a feeling, is this also usable for me? Is it, do I have the feeling if this success story is working, maybe mine, I can also provide one in the future. Okay, and the first step for this kind of center was done in September at Nanjing Normal University in China. This is you who will talk after me, and Wen Luo from the engineering department, and we are more computer scientists. This is Professor Hu from the computer science department. That means we established a research center over departments there because we have different focus, and this kind of collaboration is very important. Okay, so we already established this center in Nanjing, China. And today we also would like to discuss about this kind of center in Brno, in Almería, Spain, and Karlsruhe, Germany. I mentioned common topics are very, very important. For instance, we have one topic, quantum computing with geometric algebra, which is interesting for Nanjing, Brno, and I also had some discussions with Rafael in Brazil. He is also interested, and we can define more topics, focus on that, use synergy effects, and I think this would help a lot. So what is important for all these centers? I have some items about that. We have to discuss what is the institutional structure of the centers at specific universities. How can we communicate between us and cooperate between us? How can we cooperate with external partners such as companies? What are the main applications, topics we would like to focus on? I think very important is some kind of comprehensive ecosystem for geometric algebra computing. Then I already mentioned that common data repository. What about funding? What possibilities do we have for funding? Today, I think we can also again discuss about the name. Is, for instance, Geometric Algebra Computing Research and Application Center the best term for it? It is a bit long, to be honest, but in principle I like it. Will we have a logo in the future or whatever? So this is what we should discuss today at the end then. And okay, that's my first introduction to this topic. Do you have any questions to what I just presented?
I have a comment. Is it okay if I give a comment?
Yes, it's okay.
Yes, you can.
Yeah. So, of course, I'm very honored that Dietmar's presentation, the different mathematical toolbox so prominent. But perhaps this is like something.
Yes, but I'm also a bit sorry about what we realized.
It's not meant to provide optimized code. It's only
Yes.
meant whenever you do write an algorithm. So optimization, of course, you have to use something like GAALOP.
Yes, yes. So that's also very.
If people don't know about GAALOP.
Yeah. I think this is also very important to know which tool can be used for what. So the toolbox is wonderful for everything, I think, except of runtime performance. So if runtime performance is an issue, often the MATLAB toolbox will not be the best solution. But in any other cases, sure you can use it. It is very simple to use, and yes. So this is why I only wanted to say, in the case of runtime performance, there are other solutions needed.
Okay.
I would completely agree. Like develop the algorithm then optimize this GAALOP or
yes,
whatever.
this is why I also had this one slide, how similar the description of MATLAB with the toolbox and GAALOP is. So you can design your algorithm with a toolbox, and then if you see I need more performance, it is very easy, I would say, to translate it to GAALOP and generate optimized code.
Yes.
So thank you so much for your comments, Eka. Any other comment? Or maybe we can move. We have a lot of time then in the evening. It's about 10 minutes to discuss everything. So maybe we can move to the next presentation and so on, and let the final comments to this final discussion. And, okay. So the next presenter is. So thank you so much. The next presenter is Mr. Zhaoyuan from the Nanjing Center. So we need a minute, Mr. Yu. Are you online?
Yes.
Okay.
I'm here.
Okay. We need a minute, please. So please hold on a moment. We need a minute.
Okay. Can you see the slide I shared?
Yes. Yes. So wait.
Can I start?
Wait for a minute, please.
Okay.
¿Qué es lo que quiere hacer? ¿Listo? Okay, we are ready, so you can start, please.
Okay. Thank you. It's very honored to be. Hello. Can you see the slide now?
Yes, we can see your
Yeah,
presentation.
Okay. Maybe I need to.
Battery. So it looks like battery.
Okay, it's very honored to give an introduction of the Geometrical Algebra Computing Research and Application Center here. And we discussed a lot and learned a lot from yesterday's and today's lectures. And now in my lecture, I will provide some introduction on how I am thinking about what kind of center we need to make the geometric algebra community much easier to be accepted to both the scientific community, and the publics. So I will first use some minutes to introduce our university. It is one of the most beautiful campus in the East, and Eckhard and Dietmar has already visited our university. And our major, the geography, especially the geographical information of science, is ranked the #1 among China. So we is top 3 geographical departments in China. And one significant feature of our major is that we integrate people, most of the talented people from different disciplines, including mathematics, computer science, and earth science. And we have a lot of international groups. For example, we have the United Nations Global Geographical Information Knowledge and Innovation Center. And this is a center that tries to introduce all the geographical information science into the world to make this kind of technology to help the people to forward to a sustainable world. And we also have 2 big science projects. The first is the Deep Digital Earth International Big Science Project. This is tries to model all the Earth's history in the digital way, and it has been integrated more than 58 nations and joined all these project. And our department tries to build such kind of digital platform to support such huge different kinds of earth science data. And there's another UN Coastal Predictor program. We try to build a new information infrastructure of how we can use digital and information science to help the sustainability of coast and to make more accurate predictions and make more efficient earth science simulations, and also some educational programs. So this is why we think that we even can do something about to build a international GA education community based on some projects. I will show you that we have made the first step. And also, one of our professor has been elected as the contribution also to the Nobel Prize that only gives the 60 different persons that build the IPCC reports. So we have such kind of platform. And in GA, I do GA research during my PhD, and that is 2006, and I graduated 2011. And after that, we engaged in both the we developed a large group that every year we joined the GA conferences and also try to hold some international conferences. And this is most recently that in August 2024 that we invite Vincent, invite Warner, Eckhart, and also Dietmar to our campus and have some exchanges. And our previous works tries to integrate math, geography, and computer science with such kind of representation theory, with a unified data model and efficient data structures, as well as a computational model and a powerful analysis model to generate a new kind of next generation GIS. And what we think about is that we try to integrate different kinds of languages, including the math language, the domain-specific problem expression language as well as the computational language into a unified integrated loop. With this kind of loop, we can try to integrate different kinds of data service as well as the models in this kind of language. In this way, we build some fundamental different kinds of components. With this kind of components, we can try to assemble a very flexible platform for different purpose. That, for example, we can try to assemble these components into a GIS, and also we can assemble this into us as well as scientific visualization applications. In this way, we think that it is very easy to make this kind of platform to exchange and extend it for different kind of applications. And this is what was our development path. From the 2009 and 2016, we just to break through in theories and methods. We develop how we can express complex geographical data into data models, how we can compute the spatial relationships, the different kinds of evolution processes in under the GA framework, as well as we develop some kinds of spatial analysis models for ocean science, for earth science, and some fundamental, for example, the feature extraction, the cluster data, spatial cluster, and some trajectory analysis methods. And in 2017 to 2024, we try to verify what we developed in some large and major projects. We use it into the climate system analysis, use it into the smart urban construction, and tries to use it into traffic, oceans, and also human behaviors. And now we enter into the third stage. And in the third stage, we hope to try to find some new developments of GA research in the era of big data and artificial intelligence. This is, I think that in today, both the big data and artificial intelligence bring us a very big, very huge opportunity that we can hide a lot of complexities and the implementation way. For example, that we can use AI to help to translate the mathematical language into the efficient computational code. That in this way, people do not need to learn very hard on how to programming. They can just using their natural language and then use such kind of AI tools. We can translate these problems into computable code. And it is also very easy for us to translate the MATLAB code into GAALOP script using some kind of AI tools. So this is no problem that people can use the tools that they like. Just what we want, we just use the most familiar tools to express how we can solve the problems, and then the problem solving can be solved with the AI tools. So in this way, we hope to develop some models, tools, and to make it very easier for scientific community, the industry, as well as the education. And this is the structure of our center, and it is I'm very honored that Dietmar can be the PI, and we organize a working group from our university, including our geographical department, the Department of Computer Science, the Department of Mathematics Science, as well as the Department of Environmental and Marine Technology. There are already 5 departments joined our center. So we can do a lot of things to break the interface between different kind of disciplines. And we also very lucky that we can have lots of international consult experts. And this is our core members. As I have already said that we hope to make this center for both the scientists, the industry, as well as the educational purpose. So we invite the core member of the our university. It is a research department, and also the Jiangsu Center of Collaboration Innovation in Geographical Science, Resource Development and Application. It integrates with 11 different kinds of departments, including some leading enterprises and also some government department. They are all in the center, and I am now the executive director of this center, so I can organize this kind of different resources. And also we invite the Jiangsu German Chamber of Commerce, and I also invite Hildenbrand to visit them, and they said that they can try to help us to make resources from the industry, and also they can ask the companies about what is they needed and what's their requirements. And also we try to find some educational and industry partners. And there are 4 goals of our center. The first is spreading the knowledge of GA. And we always say that we hope to spread the knowledge of GA, but what kind of knowledge we try to spread? I think there are several different kinds of knowledge. The first is the knowledge in documents. For example, there are a lot of books that write in GA, but I think most of general publics, they do not want to read such kind of books. So they are only the knowledge in documents. And sometimes we have the knowledge in our brain that we know what is it, and we know that, but maybe we don't know how we can use it. And there are lots of knowledge in applications. For example, what we try to do is try to translate our knowledge in documents and our knowledge in brain into knowledge in applications. We use our knowledge to solve problems. And what we try to make the knowledge is knowledge in products. We can try to make this knowledge inherited into some tools, some products, for example, some softwares that everyone can use it. And when they use it, this knowledge affects, so they can solve problem much easier. And with this kind of link, we can see that we previously we just use humans to make such kind of knowledge transformation. This is why that our experts is very important. And now we think that more and more machine can try to need such kind of knowledge transformation. This is, for example, that we have automatic language translate, and also some automatic problem solving. So this is, I think, it's machine need knowledge transformation. And now with AI like the ChatGPT or other tools, we are entering into a new era that we use human-machine collaborative to make the knowledge transformation much more easier. And the second question is, how should we learn GA in the era of big data and artificial intelligence? This is why I have such kind of question. Is about that when I teach our students to make them to learn GA, they found that it is very hard to learn because they do not have the background of mathematics. And if we can we have to spread the knowledge of GA. We must to make everyone that requires GA can learn it very easier. So who is required to learn GA? I think students, scientists, engineers, and also philosophers, they have different large diversities, different of people tries to learn different perspective of the GA. And how easy and how efficient people can learn GA, because we have limitations of the cognition and learning. So we need tools that makes the learning process be easier, be interesting. And also when and where we can learn. Typically, we can only learn GA in universities or in schools, but this is a very limited space and time. So we hope that to make some products that can help us to learn the GA at any time, at any places, and even for a lifelong learning. And also, we need to increase the value and benefits of learning GA. We need to make the GA low learning cost, very high learning gain, and in a wide application field, easy to multi-applying, gifting, and integration. And the idea of spreading the knowledge of GA is, can we make GA become the Python, like Python in programming language? Most people learn Python very easily. So can we make GA like such kind of language in mathematics or related fields? For this kind of goal, we try to set up our second goal, that building intelligent tools for scientists, programming, and industry education. The core concept here is that we try to provide efficient and easy to use intelligent tools that can get the common needs for scientific exploration, software development, and industrial operations. So I hope it is a technical driven that can integrate mathematics tools as AI automation, big data analysis, as well as GA. And different group has different needs of this kind of tool. For example, in scientists, their most common task is do data modeling and visualization. And for programmers, they need intelligent code generation and debugging. And for industrial and education, they need virtual laboratories and interactive training systems. So we try to find the most common key requirements and to build a very limited, a very small enough and unified tool for these different kinds of needs. So we think that two ways is very important. The first is the underlying technology. It is like the algorithms, the computing platform, and the mathematical engine, also the computational engine. This should be done by a set of experts, and it should not be directly accessed by the users. But what the users can use is the smart user interface. We needed to use a visual operational panel that we can use the click and drag that will be very easy for everyone that can write the codes or programs. And we also try to use some natural language processing interaction, like we call, "Hi Siri, just solve this problem for me." This will be very easier for everyone can access it. So we hope to use this kind of intelligent tool to narrow the gap between the computer code and the real world impact. And the third goal is to collect successful stories. So what I think about is, what is success? I mean success that is we provide core values. This write the theory and it can solve different kinds of problems that others may solve very hard. It should be portable, that the relevant experience obtained can be effectively borrowed by different fields, by different people. And also, we must define the success about the opportunity. That if we think this is a success, maybe it not provide very large value now, but it can provide very huge opportunities. So with this kind of success, I see that yesterday, lots of the demonstration, for example, in architecture, in power system, also in some in medicine, they are all can be very good, successful stories. And what story? What story mean? We think that it should be a user need driven. For example, it must be achieved some users needs, and must be technical scalability. For example, that tools can be reused for different kinds of areas, and it should be a collaborative model that can be collaboration between developers, the users, and the domain experts. And the key problem here is that how can we collect such kind of successful stories? For example, lots of our work has already been done, but it can only be known by us. It cannot be very easily spread to the industry, to the governments, or to the general public. So we think that for a successful story, we need a conscious yet comprehensive narrative flow that should integrate the context, the challenges, the solution, the outcomes, and the most important, the impact. And we can collect these successful stories by top-down and bottom-up. Top-down is just we solve some problems that others cannot solve. This will be very easily to be learned by the scientific community and the industry community. A typical example is a DeepSeek that just use optimization in engineering and to make the cost of AI reduced a lot. So lots of people use no DeepSeek, and we can do the same thing. And another is the bottom up, that we can use scientific community driven, the user driven, as well as the education driven. We just make our users to make demonstrations and to make it spread. And the fourth goal is to provide solutions for both industries and the governments. Here, in fact, I mean here is just to integrate both the industry and the government needs with our scientific needs. That means we can driven the industry upgradation and the policy implementation through our technical innovation. And we need to bring the efficiency for enterprises, for governments, and for policymakers. So what we can provide, I think a key solution must include the three key levels. The first is the key tools. They are data components tools, productions, analysis process, modeling, simulation, as well as the collaboration systems. They are key tools that can make the solution useful. And they need to have a common base. What I mean is the AI, the geometrical, mathematical, and computational engine, and also a secure cloud computing platform. And it can have customized different kinds of interfaces. For the enterprise, they need low code development, real-time analysis dashboard. And for the government, they need visual decision-making dashboard and risk early warning models. And we we can try to find some cooperation model that to integrate both the industry research, like the enterprise demand feedback, technology interaction, and also the policy pilot verification. With this kind of solutions that we can enhance the industry with more precision and cross-sector sustainability. And for this course, we first set up a website, and this website you can access it from the internet. And we try to they are not already finished. Just you can visit it. It's in the development process, and finally we hope to build different sections for scientists, for programmers, for education, and we hope to provide some demos and press releases. And this is the infrastructure of the center. We first build this center on our GSNAP, and we provide a web server that people can access it to do some demonstrations. And we also developed a maintenance team led by Professor Wen Nuo. And this is a possible insights output that we discussed with Dietmar. And we hope to try to write a high impact paper in the Journal of Nature Review of Method Primer. And we also try to publish some papers in high impact journals like in quantum information processing or MPJ quantum information. And we hope to produce intelligent programming tools for GA computing. And we also hope to build a knowledge base and study tools for GA computing. So for this course, we just set up 7 projects. The first is AI-based intelligent GAALOP script generation. For this project, we hope to integrate the AI and the GA to automate the translates from the user-defined GA tasks into efficient GAALOP scripts to enable the stream solutions for research, education, and industry applications. We hope our tools can be an intelligent assistant that like ChatGPT to ask questions about GA, and can be a learning and education tools that you can try to make problems, try to review, try to solve problems also. And also we hope it can be a smart development tool that we hope to collect the GA with large language models to convert the natural language into GAALOP scripts and executive code that lowering the entry barriers for non-experts and accelerating the GA's learning and developing tools. And and this is the demonstration of our assistant, GAALOP assistant, that we can use this assistant to make our tools to generate code, and we can use this code using the GAALOP websites to just visualize it. So it has already been implemented. And we also developed a study model that can help people from different backgrounds and also for different kinds of geometrical algebra fields to make them can learn in a very easy and different way. For example, that for undergrad students that can only need to learn very easy GA, but for the experts, we need to provide the contents in more in depth. So we training different kinds of we training a common fundamental large language model with the fine-tune of the documents we found in GA, and then we develop different kinds of promos to make the output very customized for different kinds of people. And this is the demonstration on what's the GA knowledge This is we can ask about what is the geometrical products, and they will return the documents, return the some definitions, and also we can ask the tools to provide some problems that we can review or how we learned, and we can also try to ask the tools about some fundamental questions to try to make them to solve it into under the GA framework. And this is the development tool that we set up the GAALOP website, and now we try to using this kind of large language model to help us to translate the code from one programming language into GAALOP script. And also we in the future times we also hope to make this kind of tool like a co-pilot that can understand our code, can generate code, and can do error detection, repair, and optimization. So in this way, we can make people not in this area very easily to use such kind of tools to solve problems, and it can make an intelligent collection between the symbolic computation as well as the physical simulation. And the second project is about the smart geometrical primitive. Smart geometrical primitive expression is very, very important for the area of industry manufacturing, the imagine visualization, and the robotics, as well as in earth and ocean science. For example, that if we want to solve the dynamic processes, especially in the interface, we need some deformable geometrical primitives. This is very hard, and this is one of the key bottlenecks of current earth science system simulations, because we just only use triangles. But in fact, if we use cross-interface simulation, we need this. We need to make such kind of geometrical primitives computable, deformable, and it should have the orientations. And I think this is the advantage of our geometrical algebra that can bring us. And we have done some works on try to do multi-vector tree structure to integrate both the geometrical, the semantics, the physicals, and the relationships into a structure, into a hierarchical structure, and make it computable and customable. It has already been proved that can have more efficient in the highly dynamic conditions, for example, in evacuation and other things. And now we hope to develop the smart geometrical primitives that can support the simulation of, for example, the lines, the multi-scale structures, the data with complex relations, and also data with complex structures. We are now trying to develop some geometrical primitives that can be directly solved by the GA transformer. That in this way, we can use the advantage of the transformer structure to find the global and local collections between the complex structures of hurricane and of the ocean currents. And the third is the geometrical algebra-based quantum computing. As we know that quantum computing always use the gate to operate such kind of qubits. And why GA is maybe important for this kind of quantum computing? It is because that GA can be a natural math language for mathematics, mathematicians and physicists. to write how the quantum the quantum world be. And also it can be used as a higher dimensional calculator that for engineering and also the computer science to do some prototypes about the quantum algorithms. And after that, the GA itself can also be a quantum computation algorithm optimizer. So in this way, GA can be a unified language that can integrate both the mathematics and physics community, the computer science, and as well as the engineering science. So we hope to utilize the multivector, the spinors, to help to express the operation of qubits, to replace some fundamental gates to enhance the computational traceability and to enable high dimensional dynamics and bridge the geometrical intuition with quantum algorithms. And this is the demo that we found for 9 times that we just found maybe very interesting algorithm that can use rotation, just only use the rotation gate to build a quantum classifier. And with this kind of rotation gate, we can easily use the rotor operator directly to operate the qubits in any angle, in any orientations. This is very different from the current real quantum computer, because the real quantum computer can only rotate in constant directions, typically 2 or 3. So in this way, we can directly operate these qubits with more and more freedom, degree of freedom. And we also have some alternative algorithm that we can try to translate into under GA framework. The first is HHL. It is very widely used to solving the linear equations, and typically it has been proved that have computational advantage theoretically, but in real world quantum computer, it has not already been proved because the existence of quantum noise. But in our from our idea, I think this kind of quantum noise may be avoided if we just using the operators directly use GA. I don't know, but maybe it is a direction. And another is about some quantum neural networks. It can. This is why we try to translate the quantum neural networks into GA, is because that currently the quantum neural network has a limitation on scalability. It cannot be very have a very large depth. So, but if we can make the quantum neural network applicable, it must have a very large depth. So if we translate this kind of quantum neural network into under the GA framework, we can use the symbolic computational power to simplify such kind of very large quantum neural networks and make it possible to run in nowadays quantum hardwares. So this is what most of this kind of and in one of these kind of neural network is variational quantum circuits. It is also can be, I think, use a rotor and also some linear algebra. It will be translated. And the fourth is the smart point cloud registration. And we know that nowadays the point cloud registration is very used very widely in current industry. It should achieve the high precious arrangement through robotic geometrical transformations. And the key shortage in current point cloud registration is we need to solve the point clouds with complex structures, with higher noise, and also with multiple coordinates. For example, the upground, on-ground, as well as the underground. They have different multiple coordinates. To integrate these different kinds of point cloud in a unified sense is very challenging. And we hope to use the unified multi-vector expression framework, the complex spatial transformation, to encode some algebraic operations to simplify the modeling of this point cloud registration task to achieve the modeling and optimization goals to make efficient code generation, to improve the interoperability and computational efficiency of this point cloud registration. And the fifth is
excuse me, Professor Zhaoyuan, excuse me, we are almost running out of time, so
okay. I will be very quickly
thank you.
to see.
Thank you.
Yeah. The fifth is the software-defined geometric algebra processor. This is what Hildenbrand has already told, that we just try to translate the codes into FPGA and develop some processors. And the sixth is the application in the earth and ocean science. We try to use GA to solve the sparse data distributions, uneven data distribution, as well as the multi-scale and heterogeneity data interactions. And we now just developed some connected extraction algorithms, and also build some coastal intelligent tools. And we have built international pilot size of demonstration stations for the Qt Predict program. And also we developed a, sorry. I'm sorry. Hello?
Hello, everything's okay?
Yeah, can you, maybe I cannot,
We see your presentation.
but it cannot be changed into the next slide.
Oh.
Yeah, maybe it is because the animation is too large. Okay, can I get out and then log in? Can you see? Okay.
Yeah. No.
Yeah. I will share it to you again.
Okay.
Oh, my presentation has already been done. Okay, I will give a very quick introduction about this. It has already been finished. Yeah. And we try to find a very typical solution. Can you see the slides now?
No, you need to share your screen.
Okay. Okay. Is it okay?
Yeah.
Can you see
Yes.
yeah. Okay. And we now try to build a a project that integrates the scene, the process, and the tipping point in the coastal area. We hope to use geometric algebra to integrate both the real world, the dynamic processes like the differential equations, as well as the tipping processes in the phase space. And now we also do some knowledge spreading education. For example, we cooperate with HSE University to do a competition of the joint basic research projects, and also we invite the EID and other experts to do some education. And there are some key references. That's all. Thank you.
Thank you so much. Thank you so much for your detailed presentation, Professor Zhaoyuan. I don't know if there are any comments. Maybe we can discuss after the break. We have a lot of time to discuss everything regarding the computer center. So it's time to move to the next presenter, Mr. Oliver Rettig. Are you available?
Yes, hello.
Perfect. So you can share your screen.
Yes. I think it's not working. So excuse me, needs another moment.
No problem. We can now see your screen.
Ah, that's fine.
So see if you can make it full screen, or it's up to you.
Yes, I try it. Do you know where I can make it full screen in the PowerPoint tool?
Bottom right, bottom left. Bottom right should be full screen. Or Control L. Yeah, maybe Control L.
No.
But this is in German.
Normally.
It's no problem. No problem, Oliver. I think we can follow. We can follow the presentation. Yeah.
Okay.
Follow that. Maybe you can zoom in a bit. Yes, a bit of zoom.
Yes, I can do it.
Yeah, perfect. Yeah, it's perfect.
So then we do it this way. So excuse me about this trouble. I have tried it yesterday, but now it doesn't work again. So I don't know why. Hello to everybody. So it's really a pity that I can't stay with you at Almería, but yes, it's great that I can follow online. So very thanks to the organizers to make this possible, that I can stay online with you. My name is Oliver, and I'm a physicist. So a small introduction to me. I've made my PhD in biomechanics about arm movements while walking, and there I was confronted with a lot of geometric problems, and I could not really work in a good way with it with classical vector algebra, and I always thought there must be a better way. And years after this, now I found this in the field of robotics. I'm now working, and I've started a few years ago with working with geometric algebra in this context. So I have the problem. Why isn't it working? I cannot go to the next slide. No, it's working. So I think I have to shorten up a bit so that you can have lunch at 2 o'clock or a bit later. So I run a bit through some parts of my presentation, I think. I want to say some words about the DHBW, where I'm working, in the Robot and Human Motion Lab in concrete, and then I say some words about why geometric algebra is interesting in our lab, and then a bigger part I want to present the current status of our geometric algebra software tools project. So some of you who spent at the conference in the last summer in Amsterdam, you know something of this. I can shorten up these parts, I think. And one of the feedback of this conference was that we need a good name for it. And now we have chosen a name. Now it's called Gazelle. So you see, it's very corresponding to GAALOP, and this is also the idea, because we want to match them together. I say some words about it at the end. And the last point is about some concrete steps towards Geometric Algebra Center in Karlsruhe. I think center is a big, the word is a bit too big for it. So we are only a small group. So I think there's not so much we can really do in this context. So what it is, DHBW, it's called Duale Hochschule in Germany, and it's a corporate state university. So it's in Germany, it's in the south of Germany, the federal state of Baden-Württemberg. You see the red part in the map, and in this federal state, Karlsruhe, I have marked for you, so you have a small idea of where it is. The cooperative state university is a special form of university in Germany. So it has a degree program where it's integrated learning on job is there. The student switches between working at the company and working as a student at our university. So there's always a switch phases between and that's the specificity of it. We have 12 locations, and it's really big altogether. We have 34,000 students altogether in Baden-Württemberg at different locations, and 2,500 staff members, 10,000 lecturers. So not only the professors are the lecturers, we have a lot of lecturers which come directly from industry. And there are over 9,000 cooperative partners, mostly companies, and up to date, a very large alumni network with more than 200,000 students. And there were a lot of contacts to them after they finished their study. And Karlsruhe is a smaller part of these 12 locations. It's not one of the biggest of them, but we have about 3,500 students there, and about 1,000 partners, companies, and 73 professors, and about 700 lectures. So this is, so you're getting a small idea. So what is it where I'm working? And the concrete place is the RAM lab, the Robot and Human Motion Lab. So I switch to this slide, and this is a special lab at our location, and we try to make a symbiosis between research, teaching, and industrial cooperation. So that's a special thing in our institution. So most of the labs are only for the students, and we have a lab which makes also a lot of research, and we combine it. And so we are developing prototypes for industry, and we have a lot of collaborative projects with industry and other universities, and also a lot of projects, research projects, which are funded by public authorities. We have also student research projects, and of course we have lab experiments which are fixed and which are integrated in the typical educational part for our students. So robot and human motion lab. So that's we have funded it at 2017 when I come to this university, and I bring with me the knowledge about human motion analysis, and Professor Markus Strand, who has founded this lab with me together, comes from robotics, and so we thought that it's a good idea to combine it, and so we started with this lab 2017. So it's a new lab in our institution. So what are the main unique features in our lab? So as I said, I'm interested in motion analysis. So we have a big motion analysis system, a camera-based system with 13 Vicon cameras, where we can track a lot of spherical markers, and we are working with force plates. That's, I think, a unique feature. We place the force plates under the robot, so we can measure very accurate torques and forces from the robot's base. So that's a specific thing we do in our lab, and we work a lot with optimal control theory and use the Casady library for it, and we started to combine it with geometric algebra. So what are the applications we are working on? In principle, we have four parts where most of the projects can be organized in. So we have a lot of projects has to do with collaborative robotics. So we are interested in ergonomic and efficient human-robot interaction. A second part is robot calibration. As I said, we have a force plate to make to increase accuracy in measurement, especially of dynamic parameters. So this is what we are interested in, and for this we also use a lot of machine learning to calibrate robots. Grinding and sanding with robots is another a big topic for us, and then we have a lot of topics which has to do with sustainability. So energy consumption reduction, for example, optimization of path planning or remanufacturing processes are of interest for us. The robot and human motion lab team is very small. As I said, there's one professor, Markus Strand, the head of the robot and human motion lab, and also the head of a degree course computer science here at our location. And then that's me, and I'm working as a researcher. So I'm working on projects, typically on research projects, and I will start at 2026 with a permanent position, and then I think I have better possibilities to do some continuous work, and also the idea is to then to work more in the direction to be a small center of geometric algebra at our location. Then we have a PhD student, Florian Stöckel, who works with simulation and reality, the switch between it a lot. And we have a laboratory engineer, Silvan Müller, and Fabian Hinder, last but not least. He's the software developer and also a student of computer science. He spends a lot of time in working on the syntax of our domain-specific language for geometric algebra. So the software we develop, it's mainly driven by me and Fabian. Why we are interested in geometric algebra in our lab? So of course we see that there are a lot of often simple, detailed problems in robotics application. We can solve it though, so that it's great, and we solve a lot of these small problems for us in our concrete applications. And then we thought, oh, it will be great to have a complete robotics tool chain based on geometric algebra. So we try to re-implement all of our algorithms again in geometric algebra, with the hope that we have less switch cases and it's more robust and maybe shorter formulations and better to understand. And so that's driven by these ideas. We try to implement a complete stack for our robotics. So I think the people who works with robotics in the context of geometric algebra knows what are the main interesting things. So inverse kinematics, dynamics, so recursive Newton-Euler algorithm, that's what we have now. We have implemented some codes in the context of parameter estimation for our measurements, so friction modeling and determination of inertial parameters and other dynamics parameters. So this we have implemented. We use circle fits with geometric algebra. We also work on collision detection based on spheres, because it allows us to fasten up some calculations in the context of optimization. That's interesting. And also we have a lot of algorithms in the context of tracking motion of humans and robots, where modeling with geometric algebra is interesting. At the moment, I'm working a lot on making optimal control and model predictive control available in our software in context with geometric algebra. And we are also, it's more thinking about it. We have some ideas, but we have not really started with it, about some machine learning things. We want to start to use physical informed neural networks in the context of geometric algebra. So we want to model some differential equations in geometric algebra and use them in the training process, so that the neural network learns only things which fulfills the dynamic equations. Some ongoing activities. We have just, it's a bit funny. So we have just arrived. We are just selected as one of 3 finalists of an award with an idea which is based a bit on geometric algebra. So it's called a holistic approach for dynamic and ergonomic adaptations for robot movements using geometric algebra. So it's simply more technical things, that some technical problems we think we can solve better in this context. So it's more an idea, but maybe it brings geometric algebra more in the vision. So if we are selected here as a finalist for this prize, so maybe we can start some funded research project based on this idea. At the moment, there are 2 projects where we are waiting on the funding. So one is called AutoSyngo. So it's about handling of singularities in robotics. So it's a bit inspired by the work of Ishia Saplana. So thanks to thanks to him at this position. So I read the paper and I thought that fits perfectly for us to go some further steps in this direction. So singularities are always a big problem in our applications. Then another project is called Kirk Plus. So it's about robot calibration, and there we have the hope that we can switch all our algorithms to geometric algebra versions of it. There are also some running student research projects in the context of our geometric algebra tools project, and it's about visualization, syntax development, and also about an API for optimal control. So I think I don't have to talk not a lot about why we implement or why we try to implement another software for geometric algebra. I think there are, but maybe it needs some words. What is different to all the available tools which we typically also are using. So it's not a new additional library we implement. So we are really focus on tooling. So we have heard in the last talk about that there must be some code to create the GAALOP script, so it makes it easier to create these things, that this can be automated, and instead of basing on these existing DSLs, we are working on trying to implement I'd call it modern DSL. I mean DSL which is much more powerful than what we now have with ClueCalc or GAALOP script or all the variants we have, and with this more powerful DSL, I think then we can have much more tooling support, all these smart editing features and debugging, and will be easier. So this is what we are doing. So if you compare this with a GAALOP script, GAALOP code base, so the main difference from our approach to this is that we don't have started from the scratch. So we try to use a lot of existing very powerful frameworks. So it's the Graal virtual machine we use, and the language server protocol, and the Cascadi framework, which is well known in robotics, I think. So I don't want to go into detail of this. So only keep in mind that the idea is to bring a lot of existing frameworks together and not to start from the scratch. And so there is the idea also to integrate GAALOP into this context, and yes, so I think by this way it's easier to come in to a tool chain which we can really use in our practical applications. So that gives you a small overview about the software architecture. So you have the developer, and he interacts with its favorite integrated development environment. So it can be Visual Studio, or we use the Apache NetBeans integrated development environment, and all of these software tools have not all, but most of these software tools have nowadays a lot of interfaces which are standardized and which we use to plug in our Gazelle framework, and so it's So it's easy to come to really tooling support for our new programming language. So smart editing features. I think most of you knows what is possible nowadays with these tools. So I don't want to go into details here. It's I think the only new thing is that we try to have a DSL for geometric algebra, which really supports all these things which are typically available if you work with C++ or Python or something. So we want to make this available in the development process with geometric algebra. So most important for us, and this is where I'm nowadays very spend a lot of time in working in it, is the syntax. So if you write a program in our DSL, so it's possible to switch between different algebras, of course. So we have a special keyword at the beginning of such a program where you can define it, and we have, of course, symbols. So maybe it's a bit specific that we have Unicode symbols for a lot of operators and other things. So let's make it easier to work with it. Of course, we have assignments, and we can define functions with multiple result values, as you know, perhaps from MATLAB. We have built-in functions, and we have the semicolon syntax, you know, from GAALOP script or ClueCalc to say that we want to visualize something. We have a variant of it with a double semicolon who also can visualize OPNS representations. And then we have for loops, so that's a big thing we are working on. And we have also arrays and matrices, and if statements we haven't yet, but we will implement it soon. And then the next step will be to implement a type system, especially with subtypes of multi-vector. So that's what we are really interested in, because we think it can make working and debugging easier. So, and records, you know, maybe from Java or some other programming languages, I think it's useful, but it's not such a big thing. In our applications, we learned that we need really arrays and matrices. So that's if we start with it, we think better not to have it, though it's make the DSL small. That's better, but then after some projects we see that it's really needed. So we need arrays of scalars, for example, if we have Denavit-Hartenberg parameters or something like this in robotics. So to store some parameters inside some scalars, but we also need arrays of multivectors in robotics. So for example, if we have a 6-segment robot, then it's great if you can store for each segment the data in a part of an array. And we also need matrices. We have learned this after starting to implement dynamics in robotics. So we see in the context of inertial parameters and the calculations with it, matrix calculations are useful, and it's good to have it directly in our domain-specific language. I said that we are implementing loops in our language. So this is a very special thing, and because the usage in robotics is often an optimization thing. We are working with optimal control, and then performance is very critical. So we have implemented or we have started to implement a special possibility to work with these for loops. So in our syntax, you can define it as you know it from other programming languages, and behind it, the structure of the loop is analyzed, and then several things are determined to find out how you can optimize the loop. So it's very easy to optimize the loop if the iterations don't depend from each other. So that's the easiest thing. Then it's clear what you can do. You can separate it in different threads and can parallelize it and run it on a graphic card or whatever. But if there are dependencies, then it's you have to look deeper in detail. So a first step is then to find out if the dependency is only a dependency from the previous step. So if this is the case, then further specific optimizations can be done. And then in the last step, you can analyze which results you really want. So if you are not interested in the intermediate parts you calculate, then there are further optimizations possible. So all these things are done in the background for you. So as a developer using our DSL, you can simply use a for loop, and you don't have to think about all these details of optimization. That is done for you from our language. Another big thing for us are derivatives. So the Casady backend uses algorithmic differentiation based on forward and reverse differentiation, and this is ready to use for us, and this makes it easy to implement Jacobian and Hessian. For this, we have implemented built-ins, so it's available as a function. So this is easy to have, and it's more or less finished the work on this. And more complex it will be if you are interested in directional derivatives. So I read the chapter of the book from Durand from 2013, and I think the nomenclature of which is used with the gradient symbol, it can be a good thing to have it in our language. So we are thinking about it to implement it directly in the syntax of it. So debugging of our DSL is working as expected. So we can step through the code, and that's all working. So it's finished. The special thing is that it's also work polyglot. So if you have a program which is based on code implemented in different programming languages, so you have some files with code in our DSL and some files in Java or JavaScript or whatever, then you can combine these in a project, and you can polyglot debug through these codes. So that's really a great feature we have reached. So altogether, so this is a picture of how it looks in the NetBeans development environment, altogether with visualization in a separate window, so we can step through the code, and then if you have a semicolon on a multivector, on front of a multivector, then it's interpreted as an IPNS representation of a graphical thing, which is then visualized. So we have also a software infrastructure which allows to plug in different visualizers. So we've also tried to use the Ganja visualizer, which is also used in GAALOP. So that's a possibility, and there are specialized visualizers in the context of robotics. So WeBots, for example, that's one we want also to integrate by our API. I think I shortened up and tell not too much about specific implementation details. I said we have implemented based on Casady. So we have principally we have always we support two different versions of implementation. So one which is good to use in the development process, and one which is very fast and which can be used in the application. So this was driven by practical things that it's got to separate it. So it has to do with optimization details. So GAALOP meets Gazelle and the NetBeans development environment. So we want to bring these things together. So we are focused with Gazelle on the development process only, on the DSL, and with the Casady backend we can create only optimized C code, and this C code is expression type based. So there's a complete expression path inside based on sparse matrices, and this is a big thing in comparison with that was GAALOP do. So GAALOP creates smaller codes in different programming languages. So that's great, and that's can also be interesting for us. So we want to bring this together. So we want to be able to use the GAALOP pipeline to create optimized codes by this. Yes, what's also different is our tools are plugged in an IDE. So it's really desktop based working with it. So we have no web version of it. We don't want to implement a web version. So the web version of GAALOP is an interesting pendant for us. So I think it's a perfect match, I think, between these two technologies. So we want to link it together, and then we can have all together in to make usable in practical applications. I said some words about derivatives. I think that's a big topic in both worlds, also in GAALOP. In GAALOP, I read a few years ago in a paper from Tinkelstadt from 2017. He writes the idea, or suggested that the code generators can be used in a specific way by usage of overloading the scalar type by dual numbers to integrate some derivative implementation. So I think it's not done till today. So, but maybe somebody of you knows some more of it. And I also found some rudimentary code for coordinate-based differentiation in the code base. And so there is some starting point in implementing derivatives in GAALOP. So I think we will work on both together. So derivatives in Gazelle directly in our DSL, and also in the GAALOP code generator. So better to make it both ways together, then it's good for testing, I think. This gives you a short overview about how we can connect both together. So the red boxes you can see on the right side. So these are modules in GAALOP we want to implement. So that's the modules we have on our wish list. So the first one is we want to add an API in GAALOP that makes it easy to integrate it in an IDE, in the NetBeans IDE, for example, so that we have the user interface in the IDE integrated. So that's one thing we want to have. And then there is a really great interface in GAALOP which can read sources of the GAALOP script, but it can be used also to read other languages, and so we want to implement a parser plugin which can read our DSL, so we can use it in GAALOP. So, and we also want to implement the other way. So the code generation in GAALOP, we want to implement a specific code generator which generates code in our DSL again. And there's a specific module in GAALOP. It's called a product table generator, which is used to generate different algebras, the tables, product tables for it, and we want to make it available to be used in our Gazelle, so that we can be sure that we really have the same implementations available in both worlds, so that so if not, so it's more difficult to be sure that it's really the same. So we want to reuse it in a specific way. So we are sure that we make the same basis. So
sorry, Oliver, we are a bit late, so
yes,
I'd like to ask you if you can.
Yes, I think I can finish with this last slide. I think.
Thank you.
Yes, that's possible. So at the end I can share some ideas of concrete steps we think which are useful to come to something which we can call a geometric algebra center in Karlsruhe. So I think I can start with work on it 2026 if I start with a permanent position in our lab. So then I have more freedom to push these things. And I think the first step will be to make some to set up a website and make some promotion about that we are working on geometric algebra, and for this a GAALOP web version would be great, and we will share some of our source code on this website and so on, and writing some articles in Computer Magazine, so to make some promotion also in other contexts. So maybe this can help a bit. Also, we are thinking about some concrete workshops we want to present 2026. So we think about a specific Apache NetBeans workshop with focus on GAALOP Gazelle development and integration, and a general geometric algebra introduction workshop for our students here. And we have something special, a Girls' Day, where we also try to make something with geometric algebra. So this is some concrete things we have in mind. Also, which is concrete for us, is we want to have some specific lab experiments and lectures, and because we are a robotics lab, we will start with some applications in robotics, and maybe we can add some lab experiments for computer graphics, motion analysis, and for medicine or whatever, but this needs a lot of time for it. So I'm not sure when we can start to think in this direction. And that's the same for lectures, which are not specific for robotics. So it's I like it to have it and to bring it in other departments, but I'm not sure when we can start with such. And so I think the further work will be mainly driven by concrete research projects in geometric algebra. in the context of robotics. So we have a lot of student research projects now, and I think this can grow up, and we have funded projects in the context of robotics and motion analysis, and there we think to come more and more into it, that we integrate geometric algebra parts of in this. So this gives you some ideas what we are thinking about to come to something like a center for geometric algebra in Karlsruhe in the DHBW. And yes, then I think it's time for the next speaker, and lunch is asking for you, I think. So
okay, we can wait, no problem.
Yes.
We can wait. Thank you
Yes.
so much, Oliver. Thank you so much.
Okay.
So,
If you have some questions about the talk, maybe it's now the last time, because I have to I can't follow the rest of the workshop, because no time.
maybe,
It's a pity.
maybe some questions, some comments.
It's quite amazing the magnitude of the software you're maintaining and developing. Can you articulate why you think you need to develop a separate DSL? What were the advantages? Or why was it necessary to design your own language, and consequently, because with that comes needing to design a debugger and a runtime and all these plugins, what made you not just implement libraries and tooling in the existing languages? What were the features that made
Yes.
it?
Okay. I'm working a lot as a software developer, and I like all these smart editing features we have typically available in a programming language, and in this topic in the last years a lot of progress is done in the way we can implement DSL. So I think it's really new that it's possible to implement a DSL with so less lines of code, and this is a really great thing, and it's used in other specific topics, and so I thought it should be great to go this approach also for geometric algebra, and that's one thing, though, driven by what is available nowadays, and the other thing is that that we have the experience that it's always difficult if you implement more complex algorithms in geometric algebra to fit it in these simple available DSLs. So you can use ClueCalc or GAALOP script or something like this. So that's one way, and another way is to use some, for example, a Python way to use geometric algebra with Python library, so you can integrate it in the existing language. So that's the other way, and with our approach, I think we can have the best from both ways together, and especially in the context of optimization. We work a lot with optimization, and there it's really difficult to formulate the algorithm a way that it's easy to read, and also that it can run really fast, and then we thought, okay, if we have a DSL, we can formulate these optimization problems a way that it's easy to understand, and then we have the complete pipeline which generates optimized code from it. This is a great benefit in the projects we have. So that's the way we are thinking, and we come to the point that it's a good idea to implement a more powerful DSL. So answers this your questions, or?
Yes, I would be interested in discussing more maybe later.
Yes, okay.
I could send you an email, maybe.
Okay.
If I just for your own thoughts, do you think you would have still gone to these lengths to essentially design an entire language if, say, a Python library or other libraries had ways to generate optimized code that didn't require a DSL? Is that the main reason why this calls for?
Yes, I think it's one of the main reasons. Yes, and the second is that it's difficult to add the things we want to have in Python. So you can override some operators, but you are limited in some points, and
Yes.
and so that it's nicer. You get a nicer syntax in your code if you start with a separate DSL. So that's another reason.
Thank you. Thanks.
Okay, thank you so much again, Oliver. Now it's time to take a break for lunch. So nice presentation, and we are in touch. Okay, thank you so much. Okay. It's okay. I forgot to mention, because of we are run out of time. The presentation of Jaroslav will be after the break. Okay. Okay.
for sure. Can you hear me?
I can hear you.
Okay.
Yes. And what
But
about
it's-
the
but it's-
virtual participants? Do we have some?
Do we have virtual participants? Okay, I suppose.
Yes, I can
Yeah.
hear you.
Thank you,
for
thank you.
talking.
Thank you very much. Okay, I would like to present our Geometric Algebra Computation Center in Brno. It's mostly our scientific group. We are on the Institute of Mathematics, so my presentation will be slightly different than the others scientific centers because we don't have any equipment and we are not programmers. We just do mathematical models. So I will show you few interesting topics which are dealing with, and maybe some of them will be interested to you and you can cooperate it. But before I would like to say something about our town. Okay, the Brno is the second largest city in Czech Republic. It's a capital city of the region, which is called Morava. We have a castle, cathedral, some historical center. This is the castle. Castle was a prison many years, and it's one of the dominant of the Brno.
Nice food.
Yeah, if you are interested about the architecture, Brno is capital city of the functional architecture. So this is our only one UNESCO heritage. It's building which have been built in 20th century, and a lot of stuff was very new in this area. So there are many we have a lot of art also in street. Some of them are nice and people like it. Some of them are a bit of strange and people don't know what you think about it. Rockets, yes, yeah. It's in fact it's a clock, but nobody knows what it means. And okay, we have if you maybe we are very known for MotoGP. We host MotoGP. As in a sports, we have a very good ice hockey team, which maybe impress you, and we have a very bad soccer team. So it was just short invitation, something like this. The Brno University Technology University. We have on the end of the town. We have I think very nice and huge campus. It's exactly our group lives in the Faculty of Mechanical Engineering. This is the highest floor, highest building, and the Institute of Mathematics is in the biggest, the highest two floors, and students sometimes like to say that hell is not always in basement. And okay, so, yeah. So it was just short introduction, and now for the topics. Our the most developed topic was a control on non-holomic robotics. It means that we wrote a few papers about, we call the robotic snakes. It means that we have some links, there are wheels, and we have a non-holomic constraints, which means that the wheels can behave in the right way. There are some paper which are from last, I think, 6 or 7 years. We have more older papers, and we solve these robotic snakes and with in the middle we called robotic worm. It means that links can change their length. On the right there is a robotic snake. It's the classical mechanism, and on the left it's called trident snake mechanism. And we play in this area. We choose some planar mechanism with some non-Holmby constraint and try to solve planar inversion kinematic some control with the help of geometric algebras like a PGA or CGA. The next topic is again in robotic area. It's we try to control of the robotic arms. It's also we use a PGA, CGA. We do inversion kinematics, and we do binocular vision and something which is called visual servoing. So we have some binocular vision, and according to this binocular vision, we change the angles to have something in this camera to calibrate the camera, something like this. So this is paper of my two former PhD students, which have been published, I think, through Agaxe in Brno. So this is area of the robotics, of the mechanical systems, holonomic and non-holomics, and it's connected with engineering department because we work on the Faculty of Mechanical Engineering, and it's topic which have been developed for many years by us in this direction. We have I don't know, 20, 30 papers since we started, and we started this topic. It was maybe, remember the conference in Tartu, Dietmar, of course, remember?
No,
Dietmar not. No, it was conference in Tartu, AACA conference. This is our first paper in GA. It was published there. It was about free link robotic snake, and we deal it with point pair, and we control the point pairs of the snake. So it's first our application and topic we deal with the oldest one. And last few years we have started also to work with quantum computing, because all this application of geometric algebras before was done in a real setting. If you have a PGA, CGA, all these algebras are reals, and we was interesting how also the complex version of this algebra works. So we set ourselves, try to develop some algebra which can be useful for the quantum computing. It's the first paper, and then with Dietmar and the others, the people from the Brazil and also the other people from the Germany, we have developed this real version of it. And I would like just say very shortly how it works. It's we work in the complex algebra CGN. It means that in the complex word, the signature doesn't make a sense, because you always put an A there, and its signature doesn't make sense. So you have there is a mistake. It's G2N, not GN. You have 2N. You have 2N generators. All of them are in the square 1, and then you have to establish something which is called with pair. You can be CF and F dagger, but it's the same as you already know from the CGA 0 and infinity. It's very similar concept. It's also the with pair, but this is the with pair in the complex way, and then you establish this couple of the elements, which is called with pair, and but it's the trick is that also you have this I, and the I is F dagger, and you have to compute everything modulo this I. So this is not a direct computation, but you have to compute modulo this element. It's not surprising, because if you have a C2, it's two complex numbers. You have in fact 4 real parameters, but the block sphere is 3-dimensional. So the 1 dimension has to be lost somewhere, and it lost it in this factor algebra, and so it's really this CG2N. Is the right model for the quantum computing. And of course, if it's based on the complex number, the coefficients are complex. And if there is some reason for the application, for the simulation, to use the reals without the complex, it's necessary sometimes use just the real numbers. You have our concept of quantum register algebra, where we add 2 new elements, which are again in the square equal to 1. And this is our new I. Is nothing more than we have 2 elements, and this bivector I is in the square -1. So instead of the I, we can put this, we can put this one. So okay, and I think there is some opportunity to work in this topic. Some open question disappeared. If we was working on it, there we solve something. But if you solve something, there are new challenge stuff there. This is one thing, and in this area, in last 2 or 3 years, we was started to think what we can do more with the quantum computation, and we started to do some small research about the quantum game theory. And what is a quantum game theory? It's something which is in the diagram on the top. We have 3 players, and all of these players have their own qubit, and we entangle them. The first gate entangled 2 of them, and the second entangled different 2 of them. So we are looking for the full entanglement of these 3, and then every player can use their own gate to change her decision. And we try to model how 3 people or 3 players can to cooperate together. So the U gates means in fact I'm going to cooperate, or I'm not going to cooperate, or something middle. And this G1 and G2 means how these people are connected together. And we do some experimental numerical experimental about this setting, and we try to modulate how, if there is some entanglement between 2 players, and there is some entanglement between 2 players, who will be Shapley value. Shapley value is a common term from the game theory. So I think it's what is interesting about it, that if it's not in fact something from the quantum computing. We just want to try to use the principles of the quantum computing for the real world situation, because you know there is some paradox, Bloch paradox, about that. So what I would like to say, that we try to use the quantum game theory to model real situations, and it means that we use just the principles from the quantum computing and the model real world. So it makes sense to use geometric algebras for it, because we don't need a quantum computer. This is just the principles. And yes, this is our topic, and because everybody do power systems now, we do the same. And so what is new? We have the we have the first paper, but actually it's the first quarter, and we are happy for it. And it in the power system we try to think how to minimize the current of the sum system by the projection. By the geometric algebra, we project origin to the sum plane, and it has to if the plane if the quadratic form which is in fact definition of the geometric algebra is exactly the quadratic form which we are going to minimize, then the minimum is just the projective of the origin. This is our first principle. We are going to improve. This is what's next, generalize the optimization principles, because it's our idea. If you have some quadratic forms, and if you like to find the minimum quadratic form with respect some set of constraints, it's something which sometimes not it's too easy to handle with. But if we have a quadratic forms, the quadratic form can be quadratic form for the geometric algebra. And if the quadratic form which we are like to minimize is the quadratic form of geometric algebra, then of the constraints, if they are linear, means they have form of the hyperplanes. So we have a geometric algebra where the quadratic form is in fact the scalar product, and then we have a set of planes, and which means the constraints. So intersection of these planes, if some n minus chi dimensional subspace, and the optimal is just projection of the origin to this subspace. And this is general idea we would like to develop from the mathematical point of view, but maybe it can be helpful also in applications. And the second picture means that if we have something which is called DC offset, maybe I'm not completely correct with it, but for me it means that we have a circle which doesn't have a center in the origin. It's something like somewhere, and we would like to put the center to the origin. We can use the CGA very easily, because if you have a two sphere, it's very easy. You can just multiply them. You will receive the conformal transformation between them after some normalization. But it's the same as a rotation. If you have two planes, if you multiply them, you will receive the rotation, but the angle is 2 times you need it. So you have to. It's some normalization procedure which is not easy to do it. And then it's if you have this conformal transformation, it means that you have a combination of the rotation and dilatation, which perfectly suits these two circles, one from one to the other. I think it can be. I'm sorry. I would like to talk about it tomorrow. I think it can be used also from unbalanced system where the current is ellipsoid, is ellipses, because every ellipse has some circle inside and some circle outside. And if I would like to find the transformation between two ellipses, I can find the first transformation between circle inside and the circle outside. It's not exactly the same, but it's some step to some directions. And the way the main meaning is that it's if I have two circles, in CGA it's very easy to find the transformation between them, as in PGA it's very easy to find transformation between planes. Yeah, and it's our last application. And yeah, and because there was some discussion about the software, so I forget it, but I add the slides about the software we use it. We host one of the mirror of the GAALOP web, so this is one of the our favorite tools. And also we used the MATLAB solution Sugar, and if we have to use the Python we use this Clifford package for the Python. So, but I have to say,
Sugar is something for MATLAB.
yeah, it's for MATLAB. Sugar is for MATLAB. We have to have some tool for the MATLAB and some tool for the Python, because
yesterday I heard for the first time of this sugar, and
yeah,
I
it's
thought it would be a Python tool, but it isn't.
yeah, no, it isn't. It's MATLAB tool. It's MATLAB tool, and I think it's. I'm not sure, but if you know something different, please tell me. But it's only MATLAB tool which can provide the printing of the CGA elements.
Okay.
Drawing in CGA elements. So because we are mostly working in the area we build the scheme. We build the forward kinematics, inverse kinematics system. So we have to see what's going on geometrically. So this is free softwares which can be used also with the visual information.
And it is from what's his name, Manel?
Yeah,
Manuel?
yes,
From Manel.
it is.
Yeah,
It's yeah. You can realize. I think I'm I'm not sure. I think you can realize any signature, but the visualization work only for 2 and or 3 CGI. I think this is only 2 algebras you can visualize the results, and it's good. It's for us. It's good enough. No, it's last slide.
I have the feeling always the time is over. This is
Yeah.
no longer working.
Yeah, okay. It's, thank you.
Yeah, just a question. This sugar repository is available in
Yes,
GitHub.
yes,
That's
GitHub.
the MATLAB one.
It's
Yeah,
GitHub.
GitHub.
Yes,
Okay.
it's GitHub.
Interesting.
There is one paper on arXiv where syntax is written, and there is GitHub repository with a lot of examples and with the sources.
I think we can move to the last presentation's mine, and then we can discuss. We have more time to discuss things. Ponte donde estoy yo. Jose. And I will only give you some figures and numbers of our university, of our school, and I think that the best is to start discussing about the geometric centers. So yeah, so this is the general view of our university. As you can see, we are very close to the coast.
Wonderful.
We ask for our authorities, for the local government, if we can build a beach or so, to but they refuse that idea, because people here are intended, but they want to study, so let's focus on the study. The University of Almería is it's a bit young. Foundation is in 1986 or 85, I can't remember. We were part of the University of Granada in the past for a few years, and then we became a university as a whole. Our university is mainly focused on social science, but also on technical application, but mainly for the agriculture. So our university has a very strong background on agriculture, and as a by side also in the chemistry applied to agriculture. So for example, electrical engineering, power system engineering is something that is not so popular here. In fact, my area is electrical engineering. We were only 4 people recently. Now we have Jorge as a PhD, and 2 other people as their partial job. They were outside. They give some lectures here, but we are mainly 4 people. Curro is one of them. Alfredo is another colleague, and Raul. And we are part of the High Polytechnical School, and this is our school here. And it covers mainly what we call industrial engineering, which is electronics, electrical, mechanical, and chemical. These 4 are industrial engineering. It's very well known here in Spain. And then we have computer science, informatics, and agriculture. And the most well-known grade is agriculture. And then we have some other master's studies, again, agriculture, industrial chemistry, and computer science, informatics, and some other which are shared with another universities. And these are the figures of our school. Probably speaking 2,000 students, and 6 degrees, 5 masters, and we are not so small, because the University of Almería is about 16,000 students, but we are not in the core of our university. Our university is mainly focused on social science and something like that. So I like to put this in context, because when I started to study geometric algebra and try to find applications, it was not so easy for me, because we were small at that time. 2018, we were only 2 people working on this area. So right now we are 4. We are Jorge, also the PhD, and we try to do our best, and we focus only on theoretical applications. So we develop, as you know, some ideas for the application of geometric algebra to power system, and only after a few collaboration, one of them is with Santiago, we start to apply these ideas to the real world. So when Dietmar proposed the creation of computing centers, I was thinking, okay, computing centers, what can we do with the name computing? Because we mainly develop new ideas for the reformulation of all concepts in electrical engineering to using the language of geometric algebra, but we are not computing in that sense. But I think that, well, this is a proposal, and we can move between maybe the name of computing, maybe the applied. So we believe that maybe Almería in this case has something to say, mainly in the applied part, using the computational resources of maybe other centers. And this is the way I see our collaboration. So I would say that Almería could be a geometric algebra centers and most focus on the application of the geometric algebra, and to start with, obviously, with power systems. I have other colleagues in the University of Almería also interested in the application of geometric algebra. For example, one of my colleagues, Mr. Francisco Manzano, wants to apply all this framework to surveying, geodesy, to surveying, and geodesy, surveying, topography, or, you know. It can also be applied, something that Mr. Zhaoyuan, he applied to GIS. GIS is another topic, but it has to do with positioning satellites, surveying. Well, it's not the same, but so there are different topics that maybe converge. So from my point of view, maybe Almería could be in a different way than other centers, collaborating more in the applied. So power systems, maybe surveying. I have another colleague that maybe is interested in the application of robotics. Robotics, of course, is well developed in geometric algebra. And this is the feeling I have right now. We also contact our university in order to know what the implication of creating a new legal identity inside of a university, and they offer their support. So it looks like for the creation of the center, we will have no problems, and this is something important for me, because this was not the case before. We do not have some support in the past. Right now, it looks like well, I talked with our dean, and I told him that, okay, this is an international collaboration, and it looks like they agree that it could be a very good opportunity for everybody. So to summarize, Almería is very interested in having such a geometric algebra center. Maybe apart from computing, maybe we could add other names in order to let the other people in. And we have the support of our university, and we are a small group right now. I think we are growing because maybe 2 other people will be with us next year, new PhD, and I think we have we have the people to collaborate in other projects, not only in power system, but also, for example, I like the idea to collaborate with people like Santiago in not only on the real world application, but only on the algorithm necessary to perform efficient computations. So in that sense, it's it's computing. So because I like the idea, but I also like to add other words. But in the end, yes, we are open to start this collaboration. So from my point of view, what I want to say is that we need to agree about the way we are going to collaborate, or the way we are getting funds, and I think this is the moment that we should talk each other. Brno, Germany. Well, I suppose that Oliver and you are online.
Are they?
I think yes, they are online. So if you want, we can start such discussion and try to put ideas. And I don't know if the creation, for example, of the centers in other cities or in other places are already established or still pending to approval of their university, or this is mainly a network of intention of it is a network of real entities, real centers. I don't know. So for me, it's okay. So let's start to discuss. Okay. Thank you. So we have 2 microphones, and we can use. So we have. I think we have how much time?
1 hour.
We have 1 hour for. So maybe you have.
Yes, so Paco, my idea for your center also included Ahmad in Egypt and maybe some people from Barcelona. So I think this should not be focused only on Almería, but you can say your center is somehow.
Okay, Ahmad, I talked with Ahmad. I think he's listening on us on YouTube. At least he told me 2 hours ago, and he agreed. He's in. Regarding the people from Barcelona, it's something a bit strange because we are the small university and Barcelona is the big university. So I don't know if it has much sense that Almería is the geometric center or so, but I think they should, at least with Isia, with Manel and others, they should give their opinion, but they are eager to collaborate with us for sure. Manel told us the other day, and I don't know if we can create 2 centers or not, or we will join forces. I don't know exactly. So in this sense, Ahmad is in, but the people in Barcelona, I don't know. But I will try to contact them. Yes, sorry, I forgot that. Santiago, I think, is also in with Almería, right? Yeah. So, okay, it's impossible to create a center in every place or only 1 people, 2 people. Yes, we can. We say Almería, but
and we also do not need more centers in Spain. So 1 is enough, and all the people dealing with GA in Spain would be nice if they would.
it's not about the city or the name of the city, just the people who are working each other side by side, contacting almost every week. So in this sense, yes, Barcelona, Almería, in this case, Ebjit with Madrid and Santiago in Norway. I think
That sounds good. Yeah.
we could create a very, very nice group. And as I said before, I'd like to hear about the way of create mechanism for funding and also mechanism for collaboration between our centers. I forgot also to mention, I don't know, maybe Rafael was not connected.
I do not know.
Yeah.
I do not know what to say. So
Okay, so
I asked him before, but I did not get any answer. I do not know.
okay.
What the problem is.
Okay. So I think you mentioned about the possibility of funding with China or with European projects, or I don't know.
Yes, I only remember a proposal of you. Are you available? Yes. Some weeks ago, you made a proposal for funding for this centers. Can you explain what possibilities we have?
Yes, it is a project from the National Science Foundation of China, and it is for the excellent scientists to all around the world that out for six scientists, and I will try to find the let me see. Oh, okay. I will show it. Can you see the web page? Yeah, it is a international cooperation fund for creative research teams, and but now we have no time to submit these fundings this year, but maybe the next year. It is from it is from the interdisciplinary science, and and it can support the cooperation from the mathematics and the physical science, chemical science, life science, earth science, and engineering and material science, also information science. But in fact, we need only choose two that will be okay. And I have quit about this kind of funding. It requires it has a duration of 3 years, and the amount is about 1.2 million. It is a very huge amount, and there should be one PI and five leading scientists all around the world, and one should be in China. So in this way, in this way, we can try to think idea that can collect all our centers into a single project, and we can do from these different perspectives, and focus on one scientific problems. This is what this kind of project tries to do, and it requires all the PIs and the attendees of this project should be have higher scientific attractions. So this is the what kind of this funding, and I also try to find some small ones because this one is very huge and it seems to be very competitive. I have searched all the existing fundings. They typically the PIs. I have entry index more than 60. It has been big lamps in the scientific community. For example, some of them are awarded with very high academic awards, but this is not a must required thing. But typically, they think this is a very good, and also they should have the attendees should have very good cooperations. So maybe if we want to submit this kind of project, we need to cooperate some papers or even some small international projects. And we have some uh, country to country cooperation funds, and I will send this information to you when there's some applications. And from my perspective, that uh, I uh, I have listened to all these different kinds of presentations and introductions of the centers. I think there may be one uh, possible direction is to combine our researchers into an area like, for example, smart grid, uh, because after thinking about all these presentations, we found that we have the GIS platform, we have the GA for robotics, we have for point cloud, we have the application for smart grid, and also we have the application in medicine or VR. Maybe medicine is not very closely related to the smart grid, but the others are all closely related to the smart grid. So is it possible to us to try to uh, construct a research direction that can combine our our researchers from these different centers or different perspectives uh, to be a unified research project. In this way, I can try to make this into from China, and also you can try to make this like a EU project or country cooperation project. Then we can focus this kind of cooperation and find some fundings from both the government and from both industry. That's my opinion.
Mm.
Okay.
Are there other ideas about funding?
For sure, we also have the European Community, European Union funding. There are a lot of open or there are a lot of calls, and we should try to explore that. Uh, and in my opinion, at least, we could try to find some funds for the initial networking of the geometric centers. Um, if I understood okay, there would be Germany, Almería, Spain, Nanjing, and Brno, right? We don't know anything about Brazil. So all European countries.
I think it's not limited. It depends on the call.
I think in order to our
Can justify itself.
use the microphone.
Okay, I'm not sure, but I have seen some table which compare different European projects, and it was always mandatory to have some number of the countries. For example, 5 universities from 3 different European countries. But honestly, I don't know if it's possible to have as an additional some non-European countries. I don't know. It depends, but I just one thing. But I ask about it, and it's better to have more than 3, especially if we are going to apply for the network grants. It it would be have 6, 7 European countries. It's 3 is very 3 is minimum, and it's a very small number.
Can organize in the future. Is also member. We can, and in our laboratory we can host like some computing specialized maybe. Yeah, but about the funding is VCU. I think there is no. But we need to check every call, and maybe what is necessary is to target what is the type of call that you want to really, in which call is hosted this kind of idea. Yeah, then you have to look that part. The other is that with these calls, so sometimes it's not limited, but if it's outside the European Union countries, I think the uh, the countries that are outside probably needs to demonstrate that is self-sustained or it will be supported by their country. But it's necessary first to check the cluster or the type of calls that is going to be targeted.
Yes, I also remember some calls, including not only European countries. So we have to be sure. So maybe also, for instance, Eckhart, do you know something about some calls including Japan or or China?
Yeah, I mean, we have a European house in Tokyo, which is a sort of European embassy. They keep informing us about European Horizon projects and so on. So, sort of collaboration with Japanese researchers seems possible. How then the precise funding distribution is, who has to pay what or who can get what, I also have no detailed ideas.
I think that we should agree on the creation of the network, right? I don't know if we are in such a position. So after this meeting, at least we should agree that the centers are more or less operative, or they agree to collaborate, and of course one should be in charge of try to follow any call, try to get as much information as possible, try to share with others, and try to start the collaboration.
Yes, so I think that's very important to find a way of cooperation. How we would like to cooperate. What is the best way of collaboration? Does anybody has some ideas? What's the best?
Yeah, I think the most straightforward way is just try to publish together, because this is, for example, in my case, this is something we already know how to do it, and we always try to collaborate with other colleagues. In the end, try to publish some papers in common. I don't know. And for example, in Spain, it's quite usual that if you are about to apply for a call with other international colleagues or other international bodies, um, you you should present something in common previously. You should present some common papers, I don't know, some exchange of students, or but yes, normally this is a requirement, or if it is not a requirement, it's something that gives you points in the final grade of your call. So we should yeah we should analyze based on the information provided these days, analyze potential collaborations and try to focus on common papers if possible before any suitable call is available. And as I said before, I don't know the case in China or maybe Germany or Brno, but in Spain, if you have papers in common with other international colleagues, it's something good for your project.
Yes, but then we still have the question, how should we cooperate? So, for instance, I'm thinking about maybe a monthly discussion, online discussion, in order to identify topics for papers and this kind of stuff. Maybe this would be an idea. Maybe monthly or only every 2 months. I do not know, but I think this would be helpful in order to know what each other is doing, wants to do, and how can we cooperate in an optimal way, in some kind of optimal way. Yes. Yeah.
Sounds like you're describing a university. You say these are centers, but they're really research groups, laboratories, research laboratories, or research groups at different universities. They're not necessarily.
No, they are more. The idea is that these are some kind of groups, not only a research group, but maybe members of different research groups at one university, maybe including another university, maybe including companies. So in this sense, like it is somehow more what we would like to establish.
Well,
not
at universities, there are people who collaborate across universities. There are people who have projects that are sponsored by. I think we're just inventing research groups at universities.
Yes, yes, but we have an additional focus, as we discussed also in the session before. We would like to have some common knowledge and tools for education and so on. That's not really a topic of research groups. So it is somehow more what we would like to have.
I'm interested in hearing what exactly you envision specifically. I mean,
how is it more than a research group at a university? I know you've just said it has a particular focus on international collaboration, on interdisciplinary collaboration, but this is what universities.
This is one. Yes, this is only one focus. What we would like to do is to broaden the knowledge of geometric algebra somehow to industry and so on. Means these centers should be in the future well known for this expertise, and companies should contact them. And they currently they do not know who they should contact, because there are different research groups and they are doing very theoretical work. They do not know whether it can be interesting for them or not. And this is, in my opinion, what we need in order to broaden this knowledge and not only work at academia with geometric algebra, but hopefully in the future also in industry.
I think that, yeah, most of us, if not but Santiago maybe, we are all for the academia. So the starting point is obviously, yeah, the university, the research group, but we should look at it as a starting point, and then broaden with industry partner or whatever who wants to join. But we need to start in some point, and yes, we are all researchers. So yeah, from my point of view, this is a starting point, and we want to build something bigger, something different than the research group. But yeah, we need some time. We need to exchange ideas between us, as you said before, every, let's say, 2 months, and then try to engage others and try to build a real center, whatever it means. Yeah.
I think there should be 3 layers of our cooperation. The first is the infrastructure. We can see that we have already the common ideas about the geometrical computing. We have already infrastructures of these 4 different kinds of centers. We have some software tools like the GAALOP Webs, the Ganix, and also for our Costa and etc. So this is the first layer that we have already these different of infrastructures in the whole area of geometrical algebra computing. And the second layer is the cooperation network that we have all experts from different areas, and we have strong cooperation that because we have common collections of using the GA, but we can use GA to different kinds of things. There sometimes we need cooperation because in some problems, we should find what kind of problems is required. The international cooperation is required that for our different center to work together. A common case is about the quantum computing because it requires the people in the quantum area, in physics, and also the computing science, and also in mathematics science. So this can be an idea that we can group a network of the computing. And the third level is the cases. I think we need to focus more focus on some scientific problems and work some demos or some educational cases or write a common paper. So these three layers may need a coordination or organization method. For example, we meet together for every month or every 2 months to discuss what should be done through these different layers and what's our uh, goals. We need to make a work plan or uh, a, a work route. What is the common scientific problem we hope to solve? What is the common truth we hope to develop? And what is the education or what other scientific community we hope to attract they to join us? So maybe from these different layers and from these different organizations, it may be much clearer how we can make such kind of cooperation and make it efficient.
Discussing these workflows that you just mentioned, or some kind of plan, how will we proceed in the future? How will we cooperate, and so on? I think this would be very important. Yes.
Yes, I think it's a good idea to meet every month, 2 months online. Also, if I don't know, we can choose some topics, and if I will know that topic will be, for example, power systems, I can very easily invite people from our departments which are in the field, and they also can ask somebody from the industry which they are in the field, and we can do. And also, one my note, if my experience is that online meeting is perfect, but it's necessary to meet also in the private sometimes two one 2 times per year, something like this, and then it works.
I agree. It's good to meet and exchange research and give talks and things and do what we do in universities when we're in a research group. Um, it's just that I think I disagree with the attitude that we are taking. I mean, it sounds like we're a solution without a problem. We're trying to figure out. We are convinced we have this universally helpful thing that nobody uses, and so we're trying to convince everyone to use it. But that's not the way methods develop in industry. The methods get developed and they're picked up by engineers when they're useful, and that happens naturally.
Yes, you're
It's not because
completely,
people evangelize.
yeah. You are completely right, and this is why we try to find a cooperation with industry in this Nanjing center. So we said uh, very interesting topics can directly come from companies, and what we are just doing is somehow finding our applications, and they are not always related to industry. But if we have some connection to industry, ideas can be born in industry and then together with us be brought to some kind of new applications and to new research that we can do at the universities.
Right, but again, it's a research group with special attention to problems that happen in industry.
Yes.
But it's not like we're coming up with products and selling them to industry.
No.
Has
No, we are only an interface to industry, transfer of knowledge between industry and academia. And
but I think that happens automatically when you have good methods and good ideas. Like if it doesn't get picked up, then it's because it's still not, in the end, the best way that the people in the industry want to do things. And it's not just because they don't know about it. It's you can't force that.
Why should we force that?
I don't know. This is my impression of what the.
No. We want to have the connection to companies in order to identify what is needed in industry. What are the problems? Because
But
if
only if those
if
problems can be solved with geometric algebra.
pardon?
But we're only interested in the problems. If
Yes, sure.
the solution is
We are interested
GA.
in problems that can be solved in geometric algebra. Yes, sure.
That's kind of backwards. We come up with solutions and then let them free into academia and industry, and they'll be picked up and adopted. And that should happen automatically without us having to create so much work for ourselves.
Yes, but
centers.
my impression is that we do a lot of work at the university, but not so many people are applying it, and for me there is a big gap between, because I am very sure that academia, that industry could use much more of what we already did at university, and they can influence us. What can we do additionally? What kind of research is important? Because if not, sometimes we will doing research which is not really relevant. We think it is relevant, but it is not really, because we do not have the correct connection to industry. That's what I'm thinking.
I'd like to ask you, Santiago, because you are, I think you are the most connected person with industry than us. I'd like to hear your opinion about this. So we try to connect with the industry, and you in your laboratory you deal with them every day. I don't know. So what do you think?
On applied research, and as I presented yesterday and as discussed, like we look at for the solution that brings things to demonstrate that we can use it and apply it, and we will tackle a problem. Yeah. In this case, the problem can be tackled, and we demonstrate that it's very good to try to bring it with with the geometric algebra. Yeah. Well, what we look is solutions that are practical. if the tool is this is the best tool that we will apply. It's was very natural for me, but yeah, maybe energy and yeah, it's some applications that are there for this geometric algebra. I think in discussions we have been looking for things that where is better, because always if the other tool is easier, probably just the normal matrix multiplication and very basic transforms and solutions with the normal algebra, linear algebra, that will be continuing being there because it's the things that the people knows more. Yeah. But this kind of solutions that require this interpretation that are very high dimensional is very good for it. The other ways is that this, as I said, we demonstrated is real time. That will be very well seen. That industry don't marry techniques. They just go for the simplest thing.
So I have a question to Oliver, because we learned that Oliver in his university has a strong relation to industry, because the students are half working in the company and half at the university. How, Oliver, how do you see the chances to attract people from industry for what we are doing? Yes, 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 yes. Well, so
He didn't log out.
yeah, it seems so. It seems so.
Yeah, I think Oliver said at the end of his talk that he can't follow the rest of the program today.
But we saw him, and this is why we thought he's available. Okay.
In fact, he left the screen, the sharing screen feature left open. So yeah, but he's not here. Well, I think that at least we have the good intention, the ability to start a project, and let's see if the final result is something, yeah, that covers this connection with the industry and let's say with external players, not only the relationship between the research group to write papers. I propose that because this is an initial starting point in order to yeah, to know in a deeper way what every group is doing, what is the strong point of every group. This way we can also try to propose other ideas to other groups. For example, maybe my group or my center, which is focused on power system initially, had some problems that could be solved for the industry if all the research centers are also involved. So yeah, we need to start this. I mean, maybe we have, let's say 20 minutes up to until 6 p.m. I don't know, maybe we can stay here to debate between us internally other topics or maybe some common points.
I have a
Yeah, I also want to discuss something with the church with Czech Republic. So on that side, and maybe I don't know, Joseph, if you want to join us, and I mean, just to terminate this session and try to get this extra time for discussion between us. And yes, and big thanks to Mr. Yu Zhaoyuan. And I don't know if you will attend tomorrow, but for sure, once this workshop is end, I will try to collect all the ideas. I will send some emails with information with all the material, the PDFs. So, Mr. Zhaoyuan, thank you very much. You there?
Yeah, thank you.
Okay, so thank you so much. Thank you so much. Bye. Bye. So I think oh, sorry. My bad. Sorry, Eka. Sorry, my bad. Sorry. Are you there? Are you there, Eka?
Yes.
You're a silent person. Sorry, I could. So thank you so much, Eka, because I know this is so late in Japan. I will
Early,
try
it's
to
very early.
I will try. I will try to answer your emails. I think I will have some times later on. And
No, only when you sit at the beach and you can relax, then you can answer.
okay. So maybe we will see you tomorrow, right?
I hope so. I'll try. Yes.
Okay.
Mhm.
So thank you so much. Thank you so much.
Oh, you're welcome. You're welcome.
All right.
Just an idea. It is also interesting for you. I think I have a presentation for our GAPCO solution, and maybe it's interesting for you and for you. And for you. Yeah. Okay. So if you're interested, I can make this presentation.
I would be very interested.
Okay. Okay. So thank you so much and bye. Bye.
They are interested in the no?
I don't know.
Are they interested in the presentation of GAPCO or
Yeah,
not?
I'm interested. And you, Zhaoyuan, are you interested to get a short presentation from
Yes.
Dietmar? Okay,
Yes.
there
I'm
are
also interested. Yeah.
two online interested people.
I misunderstood. I misunderstood. Sorry. This is for you.
Can you hear me?
Yes, very well.
Yes. Please go at the and I don't know at the thank you slide. It is behind. Okay. Okay. Next slide. Okay. Uh, I need the mouse. The mouse.
I can see the slide shared.
You definitely
Maybe
share the slides.
yes.
Okay. Can I start? No. Okay. Okay, I can start. What I would like to present you now is our design for an FPGA solution. We identified a simple example for that. It is dealing with a reflection, means it is a very simple application. We reflect a sphere at a plane. Some application of conformal geometric algebra, and what you can see is the code for GAALOP for that. And okay, so A means either a point or a sphere. M is the plane, the red plane, and the question mark in GAALOP always means please compute this explicitly, because we do not have to compute everything explicitly. Something is also used only as intermediate result. Okay, what we are doing in GAALOP is we optimize this code and have an intermediate language, a low-level language. In principle, at this level, we only have sums of products. Means we compute the coefficients of the multivectors, and they are always sums of products. And we designed a specific language for that. It is called GAP, for geometric algebra parallel programs. And this is the intermediate language. In principle, you can see that what we can do at this level is set some vectors and compute the dot product, means we compute the multiplications of each element and sum it up. This is the main operation that we need if the GA algorithm is optimized. Okay. This is the complete GAP code then. Okay, and what is our GAP code design in principle? Okay. We need a host in order to configure our GAPCO unit. We have GAPCO means this is one FPGA, and on this FPGA we can have different so-called GAP units realizing some algorithms. So many algorithms can run in parallel, or maybe we have to parallelize some very important computation, and this is why all the GAP units are doing the same. Okay, a GAP unit needs some information. In principle, it translates input vectors. Maybe you have your variables of your algorithm and translates it to the result, some specific multi-vector components, whatever. So, okay, again, this is for instance, an application that can run then in one GAP unit. When working with GAALOP, sure, adding some color information and so on, you can visualize your algorithm. Okay, and then each GAP unit can consist of these dot vectors units, because we always have to compute this these sums of products. then they can be somehow combined depending on the algorithm. Oops, wrong direction. Okay, and here you can see the interface. This is GAALOP Web, online solution of GAALOP. Here you can see the algorithm, this simple reflection example, and what GAALOP is doing is to compute the configuration information for the GAPCO. Means we have our geometric algebra algorithm. We write our GAALOP script, then automatically this GAP code is produced. Here we can generate also all the other programming languages, solution, MATLAB, Python, C++, whatever, and also GAPCO configuration data. Okay, this is very detailed. I can skip this, I think. And here you can see the design of GAPCO. This design has to be done once. Means this is a design for an FPGA solution, and then everything is provided for many geometric algebra algorithm, depending on how this FPGA is configured. Okay, this is a more detailed block diagram. Okay, this is very detailed information. What is the meaning of the configuration data? That's not so important. We just submitted a paper about that for the proceedings of the Agatze conference, where we did our first real measurements, because in my book only the principal design is already described. Okay, this is very detailed. This was the paper that we wrote, the first paper about GAPCO. It is work together with people from Palermo. Silvia Francini, yes, and Salvatore Vitabile, mainly. Okay, and that's what I wanted to present. Okay, we also have ideas about the next generation, but we are also happy with what we already did. And this means, Santiago, if you're interested in this design, I'm sure we will find a way with the Palermo people in order to make a collaboration. This is only for the next design. That's not so important currently, yes. Okay, that's what I just wanted to tell you. Thank you.
Spend some time together, I think. So, Eckhard and you, I think that this is the end of the session. It's 6 p.m. So, exactly in time, yeah. So, if you don't have any comment or any observation,
look forward to tomorrow. And it was a great day today. Yeah.
Thank you so much. Bye.
Okay, bye.
Thank you. Bye. See you tomorrow.
See you tomorrow.